folks, welcome to another set of Chemistry 1 video notes. Today we're going to learn about the following standards, which cover the states of matter, particle motion, and physical and chemical changes. Let's get started. Here are some vocabulary terms that you definitely want to write down in your notes and get a firm grasp on before we really get going. A particle is just a broad term for any single piece of a substance. As you know, substances could be made of atoms or molecules. So when we talk about the particles of a substance, that just means any atom or molecule that makes up that substance. We've already learned about temperature, but to refresh your memory, temperature is the average kinetic energy of the particles in a substance. Kinetic energy is the energy due to motion. So the faster the particles move, the higher the temperature is. Since temperature is the average kinetic energy, it's an intensive property, since it doesn't depend on how much we have. Unlike temperature, thermal energy is the total kinetic energy of the particles in a substance. This is affected by how fast the particles move, but also how many particles we have. If we have the same temperature, but we increase the number of particles, the total kinetic energy, or the thermal energy, will increase. This makes it an extensive property. The word intermolecular means between molecules. So when we talk about intermolecular forces of attraction, which we'll learn more specifics on in a later set of notes, we're talking about the attractive forces between molecules, the forces that make molecules stick to one another. You've learned a lot about the states of matter over the years, some of which we'll review today. When we talk about the states of matter, we can talk about them on the microscopic scale or the macroscopic scale. In other words, we can look at the particles, microscopic, or we can look at the substance, macroscopic. Let's look at the particles first. The particles of solids, liquids, and gases are very different when we talk about how close they are together. In solids, particles are very close together, which makes compressing them nearly impossible. In liquids, particles are also really close together, which also makes them nearly impossible to compress. And, as you can see, the particles in a gas are very far apart from each other. In fact, that's one of our assumptions for the kinetic theory of gases, that the distance between gas particles is enormous when compared to the size of each individual particle. We'll learn much more about the kinetic theory of gases later this year. So, we know about how solids, liquids, and gases differ in the closeness of their particles. Let's talk about how the particles move in each state. In a solid, those particles stay in the same spot, but they can vibrate around those fixed positions. This is why a solid holds its shape. In a liquid, those particles are able to move past each other, so they'll fill up the shape of the bottom of whatever container they're in. And gases are constantly moving very quickly past each other. They also collide with each other and the walls of the container, which is how we get pressure. But that's a story for another day. Gases will fill up the entirety of whatever container they're in, not just the bottom. As you notice, regardless of whether it's a solid, liquid, or gas, the particles are always in motion. In fact, as long as we're above the theoretical temperature of absolute zero, or 0 Kelvin, there is particle motion. Once we hit absolute zero, all particle motion stops and there's no more thermal energy. You may also notice that the particles are moving more as we move from a solid to a liquid to a gas. This means that we have more thermal energy. Remember, the more our particles are moving, the more thermal energy we have. On the macroscopic scale, solids have both a volume and a shape that remains constant. This is due to those particles being in fixed positions. Liquids change their shape, but they do have a constant volume. That's because the particles of a liquid can move around, changing the shape, but they still stick close to each other, making them impossible to compress. Gases, having constantly moving and far apart particles, do not have a constant volume nor a constant shape. You're probably aware of the melting and boiling points for water, but did you know that basically every substance has a melting and boiling point? When that substance exists at a temperature below its melting point, it exists as a solid. When it has a temperature above the melting point, but still below the boiling point, it exists as a liquid. And when that substance exists at a temperature higher than its boiling point, it exists as a gas. You might ask, well, why are there specific temperatures at which the substances exist in different states? And that's a great question. When we think about how particles of a substance move at higher speeds when they have more thermal energy, we can really make some sense of it all. All particles of a substance have a certain amount of intermolecular forces that attract them to other particles in that substance. The particles like to buddy up and stick together. We call this the intermolecular force of attraction. The intermolecular force of attraction depends on the substance's shape, size, electron density, etc., so it remains constant for a certain sample of a substance. As we increase the thermal energy of the substance, or we heat it up, those particles move faster. They can start to pull away from each other. When they pull away from each other, they start to overcome those forces of attraction and allow the particles to move further apart from each other. So, in a solid, there's just not enough thermal energy or particle motion to overcome those attractive forces. That's why the particles of a solid stick together. As we heat up the substance, we have more thermal energy. This gets the thermal energy closer to overcoming those forces of attraction. Once we get past the melting point, those particles still stick together, but now they're able to move away from their fixed positions and slide past each other. This is the point in which we have a liquid. Finally, as we heat up the liquid and it begins to boil, those particles gain so much thermal energy that the forces of attraction are minimal in comparison. In this case, the particles are moving so quickly they don't have time to get stuck together, they just bounce off each other. Now we have a gas. Going from a solid to a liquid to a gas covers two phase changes, melting and vaporization. There are 6 total phase changes, or state changes. You could call them phase changes or state changes either way. As we go from solids to liquids to gases, we increase the amount of thermal energy the substance has. It's important that you understand these 6 phase changes, what they're called, what state they move from and to, and whether they're associated with an increase or decrease in thermal energy. You've learned about all these before, so I won't go into great detail. Here's a couple tricks that I find useful though. To remember sublimation, the change from a solid to a gas, I like to remember that since it starts with an S, it starts with a solid, then changes to a gas from there. Then I just remember that deposition is the opposite of that. Melting and freezing are ones you already know, and then vaporization is turning into a vapor, or gas, from the liquid state. Condensation is turning into a condensate, or a liquid, from the gas state. Then, always remember, since the particles are moving the least in a solid, solids have the least thermal energy. Gases have the most thermal energy. If you remember that the thermal energy is related to how much the particles move, that should be easy to remember. When we think about physical changes, you may recall some old definitions from 8th grade science or before. Those definitions still apply, but we're going to think a little bit more in depth about these now. In a physical change, the individual particles, either atoms or molecules, of the substance stay intact. That means there are no bonds broken or new ones formed. The only thing that changes at the particle level in a physical change is that the individual particles might be separated from each other or come closer together. That's it. Since there's no broken or newly formed bonds, we have no new substances or chemicals. We also don't lose any or gain any atoms in the process. Some examples of physical changes are the state changes that we just talked about, or when we change the shape of something, or arguably when we dissolve a substance. In a chemical change, we may take some free atoms and bond them together to form new molecules. Or we might take some molecules and break them apart into individual atoms or just smaller molecules. Either way, since bonds are being broken or formed, we end up with new and different substances or chemicals. The atoms get rearranged and bonded in a different way than they were before the change occurred. Just like in a physical change, we still don't lose any or gain any atoms. Some examples are the classic combustion reaction or burning something, an oxidation reaction often thought of as rusting, cooking an egg, or for our purposes, basically any change that includes one of the 5 indicators of a chemical change, which we'll talk about here in a few. To help visualize this, here's a wonderful illustration. In the physical change, in the top row, we have water molecules arranged in a solid, or ice. During the change, the molecules stay intact, but they start to move around and away from their highly organized structure that they started with. After the change, our water molecules are still water molecules. They're just arranged differently. If you remember when we talked about density, water is the only example that we're concerned with that has particles closer together when it's a liquid than when it's a solid. This has to do with the shape of those water molecules and the way they arrange themselves in a solid. Since the particles in solid water are a little further apart than in liquid water, ice is less dense than liquid water. This is why ice floats in water. Anyway, the important takeaway from that first row is that before, during, and after my physical change of melting, I still have water molecules throughout. In the chemical change, however, we start with water molecules. They split up into separate atoms, breaking all of their bonds, and then they get rearranged into new molecules. Before my change, I had 6 molecules that each had 1 oxygen and 2 hydrogen atoms. This gives us a total of 6 oxygens and 12 hydrogens. After the change, I had 3 molecules that each consist of 2 atoms of oxygen, the diatomic oxygen molecule, and then 6 molecules of diatomic hydrogen, for a total of 6 oxygen atoms and 12 hydrogen atoms. Just like in a physical change, I didn't lose or gain any atoms of oxygen or hydrogen. I just rearranged the way in which they were attached together. We go from water to hydrogen and oxygen gas, creating new substances. This is an example of a chemical change. The only way to ever know for sure if a chemical change occurs is to test the substance before and after the change and see if it's the same substance or if it's something new. If you can't test it because you don't have the highly expensive materials needed to test it, you can take a good guess that it's a chemical change if any of the 5 following indicators occur. If there's an unexpected color change, if it unexpectedly changes temperature or catches fire, if it produces bubbles, which means it's creating a gas, if it produces a new odor or smells different, or if it forms a precipitate, meaning it creates a new solid. It's more than likely a chemical change. Again, we can't know for sure if it's a chemical change unless we test it, but we can take a pretty good guess that a chemical change likely occurred if any of those 5 indicators happen. Well, that's all we have for today, folks. I hope you learned what you need to know about these 4 standards that we covered today. As always, if you have any questions, let me know.